Welcome to NSF's Europe's Future in Space. We're already on our 6th episode, which is kind of crazy to think about. We're covering all about the European space industry from new to old. And today we've got quite a treat for you. So without further ado, let's talk about Europe's future in space.
And here we go.
We have liftoff. Propulsion continues to be nominal.
RFA chamber pressure looks good.
Following up. Roger, roll, Atlantis.
Water towers fly! Yes!
Tango down to nominal. Flight downside speed off. Bring in speed off. Off. It's orange!
145! Oh my god! Oh my god!
Decollage. Look at that. Put that in the big bag, Eagle.
343 unfolds to go.
Indeed.
We rise together, back to the moon and beyond.
The methane would be igniting in the flare, correct?
Yikes. You good? We don't need any more of these.
Welcome back to NSF Live. We are here again on our 6th episode of this series. And you know the drill, we're going to be interviewing people and everything. But today, we have a big one because you can see here behind me, this is a green screen. Our guest today is Stefan Brieschenk. He's from Rocket Factory Augsburg. I'm sorry for butchering your name if I did it wrong. But you know, he's the COO and co-founder of the company. Thank you for being here at NSF, Stefan. And really, like, my background is a green screen, but yours is not. And I think that's probably the first thing that I should point out here. That's amazing.
Alex, Jay, good talking to you. Yes, it's actually the second stage, what we have behind us. And we're looking at the second stage from the bottom. It's just being integrated right now. This thing was already in SaxaVord for the launch attempt from last year, but it's back here now, and we're basically upgrading all the systems.
Nice. Yeah, and we had last week actually SaxaVord Spaceport here in Europe's Future in Space. We had a great chat about all of the stuff that happened there and how, you know, you guys were handling all of that issue. We'll talk about that later in the show. Of course, as always, we're gonna have questions from the chat, and so tag at NASASpaceflight, and we're gonna have our own Ryan Caden in the background picking those up. Hello, Ryan Caden. Also from the UK, I guess. But yeah, and also in the background, we're gonna have Jay Keegan producing the show. As usual, he's also being arranging these interviews, so thank you for that as well, because I definitely will not be able to do that sort of stuff. But Stefan, just like elevator pitch of RFA, it's like the usual thing that I tend to say here on this series.
Yeah, Rocket Factory Augsburg is here to build rockets like cars. We want to industrialize rockets. We want to focus on medium-sized and small rockets. We believe that if we can hit the right price point, that this is the true disruption. There are no small vehicles that are affordable. If you can industrialize a vehicle and make it affordable, most of the customers will choose that over a large rocket.
Yeah, and so the rocket that you were talking about that you have behind you, that second stage, is from the RFA ONE rocket, right? So can you give us an overview, sort of like what does it do, what sort of the capabilities, and then we'll talk about some of the specifics, because there's a few things that I'm really interested about.
Yeah, absolutely, sure. What you see here in the background right now is obviously the second stage flying, and the third stage about to separate. RFA ONE is a launch vehicle that is just at the threshold between small and medium. It has a payload of roughly 1.5 tons. What we're building right now for the first launch is the minimum viable product of that rocket. It's a bit shorter, it has less fuel, and it's capable of roughly 500 kilograms of payload.
That is, yeah. One of the things that really impressed me, Stefan, I don't know if you might want to talk about this a little bit more in detail, which is the fact that the engine, the Helix engine that is being used on the RFA ONE, is it really the first stage combustion cycle engine that is done here in Europe? Like, that's crazy to me.
Yep, there was one built in Germany before. It's called the P111, but it was meant to actually power a fighter jet. It wasn't meant to power a rocket. So we often say this is the first stage combustion engine that is actually designed for a rocket application in Europe. And that's yeah, that is outstanding. It's all about fuel efficiency in a rocket engine. It's all about producing as much thrust as possible for the lowest amount of fuel consumption. ISP is the technical parameter for it. And that is really responsible in the end for, I would say, the entire business case, how much you can lift and how much a launch will cost.
And I saw the renders. So like other people are using like carbon composites or maybe using high strength aluminum lithium alloys and things like that, but you were saying like this is stainless steel, like so you have high performance engines but also at the same time you're using steel. Like that could probably make people think, well, isn't that sort of counterintuitive?
You would think that at first. As it turns out, look, you can build rockets from composite, you can build them from aluminum, you can build them from steel. I think you can make all of this, all three of them work. But what you see here is really trying to build a launch vehicle for the lowest possible cost. And I explained to you how we're doing this. What you see here in the background is an image of the first stage, 5 motors. It's the flight version will have 9 engines. This is an image from last year where we tested the first stage with just 5 engines. But what you see here is quite interesting because it's an outcome of a real stringent cost optimization. And if you have a few minutes, I can explain it. What we basically, the entire promise that we're making to investors is that we build something that is extremely low cost in manufacturing, but something that still has significant payload. And all of this comes out of a mathematical optimization where you basically couple 3 elements. The first element is basically a trajectory optimizer, fairly straightforward, right? So mathematically, you find out what is the best way to fly into orbit. And then the second mathematical code that we use is basically a sizing tool that sizes all the structures for it, right? Basically, that takes all the loads from the trajectory, sizes all the structures, and then really cool, and this is the big breakthrough that we made 6 years ago. We coupled this to a huge cost database. So you basically, for every configuration, you can go into this cost database, and the tool finds out, okay, a tank out of this dimensions with these wall thicknesses in aluminum will cost that much. Now I combine this with gas generator motors and I see how much payload we get and I calculate what the payload costs to the customer in the end. And we basically asked this entire mathematical model, what is the simplest, what is the best way to build a rocket that maximizes payload while reducing cost? And what you see here is the outcome. Counterintuitive in some cases, also for ourselves. In the beginning, we didn't really understand why it would choose stainless steel in combination with the staged combustion rocket engines. But the answer we found out after many weeks of basically interrogating how these choices came together. And we realized there's a lot of unique combinations where the code is smart enough to say that you don't need boost pumps or pre-pumps on these staged combustion engines. That saves cost and mass. It couples that with really low-cost structures that are fully industrialized. What you see here is that these stages that we build are basically built by an existing industry that also builds brewery tanks or literally any tanks where for food processing. And these tanks have a sort of a price point with a certain design that is at a local minimum. If you make stainless tanks in this sort of design with roughly 1 to 2 millimeters, you end up with ridiculously low costs because it's fully industrialized. There are companies that make these tanks in very large numbers. And then surprisingly, the combination between really efficient motors, but motors that don't need these boost pumps, coupled with these inexpensive structures that basically can withstand slightly higher pressures and make up for the boost pump on the stage combustion engine, result in a payload cost that is simply at a minimum. And yeah, look, it's what you see here is a product that was really optimized for cost. It's not really what we wanted to build in the beginning. We did not want to build a stainless steel rocket, but let's put it this way: this local minimum of these super inexpensive structures is something that you can never get out of the entire cost equation.
Yeah, the parameters that you were looking at essentially forced you to say, okay, well, we got to choose this, right? That's
Yeah, absolutely.
essentially the whole point. Yeah.
Yeah.
And so
it's not what many engineers wanted, right? We often when we realized that this is basically the result, we were struggling because we did not want to build a stainless steel rocket. We wanted to build a really sleek-looking carbon fiber design rocket, but you could not ever get rid of these solutions that basically really optimize cost. And this is when we realized this is the combination that apparently makes for the lowest possible launch cost. Really highly efficient engines and tanks, really inexpensive tanks that are in comparison holding quite a lot of pressure to basically reduce the cost of the stage combustion motor.
yeah, that that reminds me of a certain meme floating around on the internet that is like this chart of like how to develop like a rocket engine, and it's like you have propulsion and it's a really complicated engine, then you have performance and it has a big nozzle for vacuum expansion and things like that. Like it's sort of this trade-off between all of the different things that you got to look at, right? It's and so at the beginning you sort of think, oh, it's going to be this, it's going to be that, and then as you go through yeah, just the design itself is sort of forces you to do that. Then we can see some of those stats and sort of what the Helix engines and the RFA ONE rocket. One of the things that I'm really curious, like, is this also another thing, like the number of engines, 9 in the first stage and 1 on the second stage? Is that also something that you guys sort of went through the design? Like maybe you thought different number of engines or something like that?
Yeah, absolutely. I mean, when we did all these trade-offs in the beginning, we basically threw everything to this mathematical optimizer. It tried literally all combinations, gas generator, stage combustion, any number of engines, also any number of stages, any type of materials. And we iterated literally millions of different combinations. And this is basically what you see here is the winner. The number of engines on the first stage surprisingly isn't that strong of a function. You could also make you could also use 10, 11, 12. There are some advantages of using more, especially if you want to land the first stage again, because 1 out of 9 engines is a little bit too much thrust to do a landing burn of a first stage. There you would go for a higher number of motors. But this is surprisingly, the number of engines on the first stage is a very low sensitivity, meaning that if you basically force the code to give you the answers for 10, 11, or 12 engines, the payload doesn't change much. It hardly changes at all. What it does, it compensates for basically putting more fuel in the first stage and less fuel than in the second stage. So this was a surprising learning to us that actually the number of motors on the first stage is not a strong design parameter, and you can compensate with many other parameters to build a rocket that is equally as performant. 9 for us was a lot because obviously these engines are quite expensive to make. They are quite complex, and the bottom line is that 9 plus 1 is 10 engines for launch. Takes a lot of time to put them together, but this is what we have right now, and we are just in the process now to build the second batch of motors for this first test flight.
I gotta ask, because it's a lot of engines, but also do you get something out of having to build a lot of engines and like, you know, serial production kind of thing of, you know, economies of scale, for example, and being able to have multiple engines also could give you more data. Like, did you also got that into the equation of, you know, the trade-offs, I guess?
Yeah, absolutely. I mean, this is the cool thing, or the good thing about using engine clusters on the first stage is that the engine that you're developing is smaller. And if you look at the non-recurring costs of an engine development program, it's scaling with basically the thrust to the power of anywhere between 2 to something to the power of 3. So developing large engines is super expensive. It takes forever. And this is something that we factored in. We basically said, look, let's express the non-recurring cost also. And you basically want to stick to an engine that is somewhat easy to manufacture. And what you see here, what you see with Helix is this is the largest engine that we could basically make in a simple fashion with all the processes that we have in place, a lot of them coming from automotive. I always say this is basically, it's a rocket engine that is roughly the same mass of a complex car engine, weighs roughly 200 kilograms, but it uses a lot more fuel, 30 kilograms per second, and it has a lot more power. One of those motors produces roughly 500,000 horsepower in total, and it's about 30% thermally efficient. So 30% of that is turned into thrust, and the rest is noise and heat.
Wow. Yeah. One of the things as well, because a lot of people are already asking, I'm getting ahead of Ryan here, but you know, our title was about the first launch from UK soil or something like that, I think.
Yeah.
And people might be wondering, like, this is a German company, but you guys are launching from the UK. Like, how did you decide to get to that point? Like, maybe instead using other locations, like, yeah, that kind of decision.
Yeah, so first, we're a pretty international company. You might have heard we're roughly about 250 people right now. We come from actually 40 different nations. We speak English all day long. It's a pretty international company. Yes, we are Bavarian, German, but we are mostly European. And it's in the name, Augsburg. At the end of the day, look, we do the best thing, that we do whatever ends up in the best possible business case. And SaxaVord is a great location to launch from. A lot of these payloads are seeking to launch into a polar or sun-synchronous orbit. And SaxaVord, which is at the very, very northern point of the UK, is sort of the ideal location to do that. And yeah, it's also that the UK has a lot of industrial capability to make this work. There are lots of companies that work in offshore applications, and we realized it's actually quite straightforward to work with some of these suppliers and companies to build up this launch site there. It's also, SaxaVord is a private sort of spaceport. That was important to us, that there is some drive to really make things basically work quickly and get to an actual business as quickly as somehow possible.
Yeah, we had SaxaVord last week, and Debbie Strang, she actually talked about, you know, that coordination being private. It's a little bit easier in some of the aspects and things like that. Let's go now to those questions with Ryan, talking about the UK here, because I'm really curious about what people are already asking in chat.
Yeah, so we've got a couple questions. First up, Henry in Space asking, related to SaxaVord, we were told last week there's ferries, there's flights, but how do you actually get a rocket from Germany to SaxaVord? Like, personally, like, are you putting this rocket through the Channel Tunnel under the English Channel? Like, how do you get the rocket to the UK?
Yeah, good question. It's actually the first rocket we are building is small enough to basically fit on a truck. And as a matter of fact, the truck loads the first stage up here in Augsburg, and it basically goes over a couple of ferries, and it ends up in SaxaVord on the same truck. There's also other means. We can, here from Augsburg, you can, very close by, we have a harbor, and we can basically make diameters up to 4 meters and ship them basically to any place in the Earth, because it's only roughly a 1 hour drive from here to a harbor that's in a location where you can go anywhere you want. But this, you can see this on the background. This is our team writing the names down on the crate that contains the first stage. I hate this crate, was expensive, even though it's made out of wood. We wanted to build a sauna from it, but that plan didn't come true, because when we opened that box in SaxaVord, unfortunately, it could not be assembled anymore. But you see the truck here, it's leaving, and it's actually going on the German Autobahn right now, right there. And it just takes 3 days, and it's in SaxaVord.
Awesome. And finally, for now, Optish TV is asking, what upgrades have you been making to stage 2 and the entire rocket? Because as you were saying earlier, the second stage behind you, I think you said that was originally actually stationed in SaxaVord when you were static firing your first stage last year. So what upgrades are you making? You obviously brought it back to the factory now.
Yeah, so you can see the second stage here on the truck. It's what you see behind me is very much the same thing, but what we have done is we have learned from some of these operations, a lot of these operations not related to the failure, but just in general, basically performing a hot fire. And what we want to make sure is that these operations are as bulletproof as possible, and that requires a lot of coding, and it requires a lot of system to sort of work together or almost autonomously. And this is why a lot of these systems basically received small tweaks to make them more robust. The general thing you see here on the stainless section, it's these stages have common bulkheads, and this is not difficult, but it requires basically when you vent the stage, for instance, when the stage is full of pressure and you vent it, you want to make sure that you vent the compartment that basically has the bulkhead in the normal direction, slower than you vent the bottom compartment, otherwise the bulkhead inverses. Not sure if this is clear now from what I'm saying, but all of this is happening basically in the computer, and you have to size a whole lot of orifices, a whole lot of valves. You have to code it all up to make sure that all of this happens automatically when you say press the stage or when you say stop the stage, an emergency event. And this basically received a whole bunch of small upgrades, not large upgrades, but there are thousands of small details that you have to get right to basically make sure that you can hand over this operation more or less to a computer and just press a button and make sure the thing basically fills up with propellant, presses itself, and launches.
That's pretty cool. Alex, back to you.
Yeah, there we go. I was muted there. I have more questions, but I think since we touched on the SaxaVord Spaceport, we should probably talk about the testing that you guys did, because we're talking about the RFA ONE rocket and things like that. You guys already had hardware there. What happened there?
Yeah, we basically, for those who don't know, we had the first stage there. You've seen it before. We first equipped it with only 5 motors. We tested that. All of these were qualification tests. This is a very important thing to note. Qualification means you basically stress test it. You subject the stage to loads that are higher than what the stage sees in flight. This is basically key to making successful space hardware. You always test it way harder than what you will see on flight day. So flight day is easy and you don't have to worry about things going wrong. What you see here in terms of stress testing is basically in pressure and temperature of the propellants. All of these first stage tests use basically a very, very high temperature in the liquid oxygen, and we use the lowest possible pressures in the stage. You can see the stage is barely filled with propellant. That also means there's a lot of structural load on it. And long story short, these were stress tests. And in the 9-engine test, one of the LOX turbopumps exploded, and we lost the stage, unfortunately. There was a fire suppression system. I think this was the biggest learning, but that fire suppression system had issues, and it didn't basically kick in as quickly as we needed it. And unfortunately, we lost the entire stage. And now in hindsight, it still hurts me. There's one of these burnt engines at the entrance, and every day I walk in, it's the first thing that hits me and motivates me on one side, but really creates some pain in my heart on the other end.
Yeah, I can understand that, because it's like you were very close, right? Like you were, I believe you were already shipping that second stage, or it was already there for the launch, right?
Yeah, everything was there, fairing, third stage and second stage, and everything was acceptance tested, except the first stage. But again, now in hindsight, we learned so many things from it. We had more than 200 active sort of learnings. A lot of them required only small tweaks. A lot of them were operational tweaks. But overall, it's what we have now is a much improved product. I believe it's significantly better. Here you can see one of the a big flame coming out on the side. This is from engine number 5 that basically caught up on fire. And you have seen that the flame continued to get to go. Somehow the pre-valves there didn't close. But you can see this blaze. You can't stop it at this point, right? Once every pixel of the camera is white, there's nothing you can do anymore.
Yeah, I remember you guys released I think it was like a several minute video that I mean, you're actually talking in that video about what happened with the test, and this is something that we don't see a lot out there with most of the private companies, that you just come out and release all of these footage out of the blue and be like, here's our explosion, right? Like that's not usual. But also at the same time, is there anything else that you have learned even more since that video came out about the failure? Like what else happened there? And like, is there any fixes that you might have put in place that you can talk about, that it's not,
Yeah, look, the first thing is obviously fixing or basically improving the turbo pump. Again, important to understand, it was a qualification test. We pushed the pump to the extreme edge of where it could operate. And these turbo pumps, the liquid oxygen turbo pump is probably the most difficult thing in a rocket, especially if you have a staged combustion engine. It pumps up, it creates extremely high pressures, close to 400 bar. And long story short, if there's any friction in it that you basically pair with pockets of gaseous oxygen, then it's basically over. And it was interesting for us because we had a lot of these engines tested in Sweden. We do all the engine tests in Sweden, and we have driven this pump into this extreme limit many times before. We have actually seen some failures that were quite similar in the engine testing. But what was a surprise to us is that in this test, the pump basically didn't make it. But look, long story short, it was a stress test. It went wrong. We have made some improvements, but it's surprising now if you look at it all, how small these improvements were. There are basically a lot of small changes that have really, really big effects, where you can really, I can't go into the details now and show you hardware, but you would immediately understand that, like, it's just the small details that change, and it makes a certain failure absolutely impossible to occur. And yeah, look, on the transparency, we want to be as transparent as possible. Also, for the team that's working here day and night, makes no sense in our view to basically brush things under the carpet or appear better than you are. The reality is there are more rocket companies that are failing than there are rocket companies that will be successful. And there is no point in trying to look better than you potentially are. We had a mishap. We've learned a ton from it. And that's just what it is. The cool thing, really, and for me, one of the coolest job is for the data engineers, right? Because they sit there, they get the data in the live stream, similar to how we're doing this video right now, and they can figure out within literally minutes which parameters were totally off. And they know within a very short period of time, with quite high certainty, what went wrong. So there is no point in waiting and sort of discussing what we should say or what we shouldn't say. It's crystal clear. It's all the data is there, and just within minutes, within minutes and within hours, you can basically understand what happened there.
Yeah, that is.
Oh yeah, that's just the statement we issued, right?
Exactly. Yeah, that is the statement. And one of the things that happened, because obviously the very first news came out like from BBC, I think it was, and it was like minutes afterwards. But this was like official within two
Yeah.
hours of the mishap, right? And like in the video was I think like a week or so afterwards, like you guys put together all of that and made the effort of actually having you explain this is what happened, this is and going through everything. And I think that's something that it's really great, that should be done more often, I think, in the industry, because
Absolutely.
Everybody can also learn from everybody, right? It's that sort of thing as well, that it makes us all a lot better. One of the other things as well that I wanted to ask, because you guys had that failure, but like, was that really like the last thing that you planned before putting together the second stage and the first stage, the payload and everything, and just light up and go, or like, was there anything else that you were planning to do?
Yeah, so on the transparency part again, look, for us, it's super important to also attract the best talent out there. The best talent you get if you're completely transparent and open, right? And this is really, we've probably done it more for the people working here and for the talent, for the future potential talent that it will be working for us in the future than for anything else. This is really the core why we want to be so open and so honest, and basically put the facts out there. As for the test, yes, we basically were planning to do this hot firing test with 9 engines. Again, almost no propellant in the stage, which is the most extreme stress test you can do. And long story short, after this test, we would have put the stage down, integrated stage 2 and the orbital stage, and we would have proceeded to a complete vehicle, where the flight computer is basically sitting in the vehicle and commanding all the procedures by itself. It's quite different if you have a first stage up there. Obviously, the flight computer or the commanding is done from a different physical location. The setup is different, and there's still quite a lot of tests to go through, obviously, once you have the assembled vehicle on the pad. But we got relatively close. Whether or not we could have launched last year, I can't answer now. But we are fairly certain that by now we would have succeeded with our first launch.
Yeah, and going a bit, probably a bit more of the technical side of things, because I see this Launchpad over my shoulder. I guess this is the green screen version of it. The pad doesn't show like a strong back or like a chopstick system or something like that to mate the two stages together and the payload and everything. Like, how is that gonna work once you guys come back again and put together your next rocket?
Yeah, well, what you see here in the background is basically the first part of the umbilical tower. Can you see that yellow construction crane there on the side? And yeah, this is obviously not completely built yet. This is basically, we built the section that was required to do the first stage test, because for us, that is the most critical data. We really needed data from this first stage test, pushing the first stage to the absolute edge to understand what it can do and where we can improve. And that is basically the data we've got. Super, super important. We're very glad that we received this data. But what will happen for the actual flight is that the vehicle is integrated in the hangar, and then the entire stage is lifted on the pad with a mobile crane, simply because that's the fastest way, also the least expensive way to do it. Look, there's 100 ways how you can put a rocket on a pad. We have just simply chosen the fastest and cheapest way to do it, and that's just asking a crane company to do the job for us.
Yeah, it's what you mentioned, right? About trying to be as cost effective as possible at the end of the day. Like, instead of having to build some weird contraption or something like that, you just go for the simple thing and probably the cheapest, maybe. I don't know. haven't looked into the economics of that. I'm sure you guys have. One of the other things as well is, so once you fly this rocket, right? A lot of people are wondering, because you guys say it's reusable, that first stage, right?
Mhm.
Like, how are you going to try and recover that?
That is something I can't tell because we're
Oh.
in a tight competition. But look, we looked at many ways how to recover. We think some make more sense than others. We put a lot of effort and a lot of different talent on the topic of how to recover. And surprisingly, there are some methods that basically people align with. So independently, some really smart brains that we employ came to the same conclusion. But I can't spoil the beans now how we're doing it. But it's going to be super exciting. Of course, we need to be careful not to get too distracted, right? The rocket is made to be recovered. But now for the first flight and for the second flight, we focus fully on actually getting to orbit first. It's incredibly difficult to get small rockets into orbit. A lot of people don't know the fact that rocket scaling is anything but easy. The larger you make a rocket, the easier you have it. If you make the rocket the size of a pen, imagine this is getting close to impossible. It would have to overcome its own length so many times to get to the same destination. That it's simply not possible to build a rocket at a really small scale anymore. So in a lot of senses, smaller rockets are more difficult to get into orbit than larger ones. And we need to focus now that we get to orbit. Said it before, there are more rocket companies that are failing than rocket companies that are succeeding. And we need to be super focused on the goal of getting to orbit and not get distracted by how the rocket is actually erected on the pad or reusability or many of these other topics that come around and want to distract you.
Yeah, that's very understandable. And it's one of those things that it's like, should I focus now on this or maybe leave it that later down the line? Like that makes a lot of sense. And there's of course now the question of like, okay, now what's the road to that, trying again, getting that launch up and being able to get off the ground.
Yeah, absolutely. So, like I said, a lot of small details have changed in the oxygen turbo pump. A lot of small details have changed on the rocket engine, but overall, the entire construction hasn't changed. It's details that you really need to understand and be fully in the detail to understand the changes. But what we're doing right now is simply we are building the next batch of engines. We produced quite a lot of engines for our company size at this point. Again, we're roughly 250 people. We've built roughly 30 engines so far, if you count all the prototype engines. And the engine is by far the most industrialized aspect, but it's still difficult to build them. It's still a lot of parts. It has roughly a rocket engine like this. A Helix has roughly 3,000 parts if you really count every single part. But there are roughly 20, 30 parts that really are very, very difficult to manufacture, parts that have 30 or more production steps in them. And it just takes some time to industrialize that and basically pump these things out quickly.
Yeah. And are you guys going to be repeating some of these tests that you already did with the previous stage, or are you going to skip some of those? Oh, you're going to be repeating them?
Yeah, we will repeat some of them. Obviously, now we found certain limits. We have understood why the turbo pump has basically failed. Many reasons, as you would expect from a failure like this. It is typically not just one thing, especially if you have done so many tests before. It's a couple of things that basically aligned, and we have basically made improvements on all of them. This extreme stress test, we will not repeat like this. We will have more margin for the next tests that we will do. But what we will definitely do is ignite all 9 engines on that same pad before flight, and then basically get to a first flight as quickly as possible. We want to fly definitely this year. And this is This is the goal.
Yeah, I'm curious about a few other things as well, for that road to the first flight. But I'm gonna come back to Ryan because I think we have a few more questions from chat.
Yeah. Speaking kind of to your launch site, Optish again with a question asking, do you have any plans for other launch sites to do kind of equatorial low Earth orbit missions? Is Kourou, French Guiana, anywhere on your roadmap or anywhere else, I assume?
Absolutely. Look, the honest answer is let's be super careful not to get distracted. If you fly a complete equatorial sort of mission, you have roughly anywhere between 6 to 7% more payload than if you fly polar. Not worth the discussion at this point in time. The reality is once the vehicle gets orbital and we have something that can put payload into orbit, then we can consider operating from multiple launch sites. But for this, at this point in time, we need to focus on making this thing work and getting to orbit. Everything else would be a distraction, but of course it's possible. You've seen the launch site in particular. The details here are blatantly obvious. If you look at this launch pad, you realize there's not a lot of concrete works. Concrete works is basically the big struggle. That's what makes everything super expensive. But our entire launch platform is built on basically a very small concrete pad. And you can see how easy it would be to replicate that anywhere else. And that is really key for us to make sure that you build a launch site that is simple, that you can replicate many, many times in many different places and really offer the customer a low-cost launch service.
And also speaking about things in the future, I have a suspicion it might be a similar answer. Kai is asking, are you working on anything for a bigger rocket yet, or are you just focusing on RFA ONE for the moment?
I say to all of my engineers, please do not look at any other vehicle than RFA ONE. But obviously, you see, this is the difficulty in engineering is to basically focus, and design the same part 10 times before it's really at the optimum. It's super easy to basically design something and then lose interest and then go and do the next thing. This is it's like human intuition. You always want to do the next most exciting thing. But the real hard part is basically always going back and just making this one component better and better and better, improving. Change a small tolerance here, change an acceptance test procedure here, change something there to really hone in part by part. That's the difficult thing. Team upstairs now is super excited to be working on a large launch vehicle. But if I see anything on the computers, I need to shut it down. I need to focus people on that first vehicle. This is really, really key. But the reality is, look, we have all the tools to basically improve engine performance. We think that the engine Helix can easily be upgraded to roughly twice the thrust. Of course, when I say easily, it's still a big development project, but we think that's basically within the design envelope. Very similar if you look at other rocket companies, how they scaled up engine performance. And that would be the logical next step. For us, the most important thing now is not to get distracted by the super exciting things, but to actually hone in the production, acceptance testing, and making that bulletproof.
Awesome. And a final one for now. Hans Skitz asking, what is your cooperation with ESA like? Is the European Space Agency supporting you in any way? How's that all developing in Europe at the moment?
Yes, look, we are super glad, obviously, to have the German Space Agency DLR and the European Space Agency ESA to be supporting us. That's incredible, obviously, super important. You probably know that the European Space Agency's funding is not as big as the NASA's funding in the US. It's by far smaller, but the relationship there is very good, and we're super glad that we're working together on projects, because for me it's always, even if Rocket Factory would not work, the important thing is that the country and the continent didn't lose that money, right? So this is it has to result in at least a couple in designs and in knowledge and in engineering that is basically that is of some value for the future for other rocket companies. And this is why this is always a big thought. We have no problem with sharing information. Typically, when you do a European Space Agency contract, you have to share a lot of details. Fully open to that. I want to share that openly. I obviously don't want to give it to a competitor, but I think the way how this is organized in Europe now is fairly good, because what we do here since 6 years, some of these activities are supported substantially by the European Space Agency, and the way how this is set up, where they basically are not completely hands off, but they're giving us a lot of freedom to basically try to reinvent and innovate. And I think this is really good. And last but not least, I think one of the strongest aspects is that there's a lot of experienced people in the European Space Agency that you can ask how things work. And it's always, we strongly believe that there is a best of both worlds. You know, it's like a startup that tries to do everything differently and new, but then also taking into account all the learnings. It would be foolish to think that you can do everything better and that all the experienced people have basically who have done that in the past would not have a significant contribution to make. The reality is you need to combine this best of both worlds, and we are super happy with this situation with the European Space Agency.
Yeah, awesome. Alex, I will throw it back to you.
Okay, yeah, because we're talking about many things, of course, because everything is connected, right? As we usually say. And one of the things that I'm curious about, because we were talking before about the pad, when you guys had the failure, right, on the pad, that fire. Okay, so it happened. Now, what's the sort of thing that you had to do to be able to prepare all of that now for that first flight, and like what's the status right now of that launch pad?
Yeah, look. The really cool thing is, if you look at this pad, there wasn't much to begin with. It's basically what you see there is a steel structure, super simple. In fact, it's got so much steel in it that nothing takes a lot of damage, even if a first stage burns down. The umbilical tower wasn't really built, so we actually, in all honesty, we lost very little on the launch side. Of course, all the cabling and all the harnessing has to be redone, but at the same time, I think we saved a lot of money from not building a separate first stage test site. What you see here is basically the pad, and we built up the pad to the point where it's just good enough for a first stage test. And yeah, it's basically on the pad. There is some work left to obviously put it back together, but what you see here is mostly fuel combusting. And not a lot of launch site combusting.
Yeah, it's sort of the same sort of deal that Debbie, when she was here last week, she talked about, that the construction of the pad was robust enough that, major structures were sort of largely undamaged, and it was more about the wiring and things like that. And, I'm surprised because we went twice with the public questions, and nobody has asked the big one, or at least I think it's a big one. When are you planning to launch?
This year, we want to launch this year, and like I said, we're just basically in the process of making the new improved versions of Helix. And for us, the most important thing is launching this year. We do not have an exact launch window yet, but the most important thing now was for us that within a 6-month period, we close out all of these tickets that we have learned from this first stage test. Not just from the failure, but from the complete first stage testing campaign. Like I mentioned before, we had roughly 200 tickets, and we closed out all of them now within the 6-month period. And we are now in a point where we can look at literally every single system and say, wow, every system has significant improvements. All the learnings came in, and what we're building now is significantly better and more robust, more reliable. And yeah, this is it. 6 months after the failure, and we're probably say anywhere between 6 and 8 months basically before the first launch attempt.
And is the hardware like following along for the following flights? Like, do you guys plan to have a very quick cadence afterwards, or just gonna take your time, go through all the data and everything? Like, what's that sort of planning for future flights as well?
Yeah, so we are building 2 vehicles now. Basically, you have to be careful. If you want to be money efficient, you have to be really careful not to start with all of this industrialization too early. Because the reality is, with rocketry hardware, you have to understand that the first designs you do, they will not live very long. The reality is that you have to build at least 10 sets of hardware and basically redesign a couple of times before you get somewhere that can basically get to orbit in an efficient fashion. So it's, in our view, it's super important that you do not spend a lot of money on industrialization in the beginning, and you really focus on iterating the technology. I always say that when you see a rocket taking off, only between 1 and 2% of that total mass ends up in orbit. If every engineer makes a 1-2% mistake in their designs, then simply it will not work. And it's super important that you focus on the technology iteration in the beginning, not on basically scaling up a production line that will produce prototypes that will become obsolete very quickly. And the bottom line for us is get to a first working product for the least amount of investment, right? We want to be money efficient because we believe that's the most important thing. It's not so much about being the fastest, although we were in a pretty good situation. We have spent significantly less money than some of the other launcher companies out there. I believe we got to this first stage test significantly faster than a lot of others did. But again, the key is iterate the technology and make the technology robust, inexpensive, and yeah, for that you have to iterate. You have to iterate and iterate in the beginning, and it makes little sense to build up huge production capabilities. That will come after, basically, like I said, hardware prototypes number 20 plus. That's when you can say, look, we believe we have so much confidence in it that we can basically plan ahead for producing many of them.
Yeah, I guess also the construction of the rocket being stainless steel kind of helps as well with that. We know that at least SpaceX sort of used that as their excuse to use that on Starship as well, because it's sort of this huge rocket that they were building. So, well, at least it's stainless steel, so it's cheap and easy to handle and everything. And so, but yeah, that's definitely one of those things that you know you guys can benefit from essentially. I do have a question though, because we are NSF and we like live streaming launches. Are you guys live streaming launches?
I'm sure we do. You have to ask Jonas, who's somewhere around here, who's managing all of this. But I'm sure we're live streaming it. Look, there's nothing to hide. The world shall see what we're doing. Again, we're trying to do this as transparently as somehow possible. We really also feel obliged to do that. Again, we have some contracts from ESA. This is more or less public taxpayers' money. I do not want to accept this money and then sort of not be honest and transparent what we do with it, right? Everyone shall see what these people here are doing, what goes wrong and what goes right. We believe that this is the right way to continue, and I'm sure that we will live stream and we will not try to hide anything, or you can see everything that we're doing.
Yeah, last week when I asked Debbie, like, is there internet connection there or anything like that, right?
There is an internet connection there. The more important connection is between mission control and the rocket. We had challenges with that last year. Yeah, I hope that the connection between mission control and the rocket is significantly better than the internet connection to SaxaVord. But you will at least see a frame every now and then, I'm sure.
Yeah, we'll definitely try our best, of course. I already told Debbie we should go out there and put some SaxaVord live kind of live
Yeah.
stream. But anyways,
You probably noticed when the failure happened, there's a very good viewing platform or very good viewing spot where you can see it all happening. And yeah, that's an amazing spot. I'm still tempted to go there instead of being in mission control. I suppose my engineers don't want me to be there anyway. So maybe we will see each other there on launch day.
And now you mentioned that, like, do you have mission control there? Do you have a launch control center, mission control center, sort of like in the US that they have a launch control center near the pad, but then they have a mission control center sort of at their headquarters, sort of thing? How is that going to work once you start flying from there?
I think there is a building that is being constructed that is basically the location where you do everything from. But if you go back to this video that you have played, last year we just had a shipping container, and we realized 8 people in that shipping container is too much. So we definitely need a little bit more space. But yeah, it's going to be it's going to be a quite professional environment up there, because a proper mission control center is built where, yeah, this is the container I'm mentioning. This is really the cheapest and least expensive way to do this hot fire. Just because it's inexpensive doesn't mean it's not robust. There's a lot of redundant data connections there to the vehicle. There's lots of redundancy in the code. The stage, if it loses connection to these screens and does an emergency shutdown. So while it looks inexpensive, the actual operation of it all is quite robust. When the failure happened, everything that you have basically seen afterwards happened more or less autonomously. It went through all the hundreds of if functions and made the many hundred choices that we basically put into the onboard sequences. Wasn't enough water to delete the fire, but that will hopefully work better next time around.
Yeah, let's see. I'm really curious about what sort of the possibilities there to be able to gather at least some kind of viewership there from SaxaVord. But I want to switch topics, because I know you've talked about focusing and like trying to get to that first flight and go through all of that and just focus on RFA ONE. But I know there was a certain thing that you guys did for ESA. I think it was ESA, the protein study, I think it was. And we actually featured that. We have a weekly show about news in space called This Week in Spaceflight. We had a 2 or 3 minute rundown of the things that you guys proposed on that study. And like, was that something anywhere real, or is that like, well, if we were to do a fully reusable rocket, this is how it will look like, right? Like, how that even came to be?
Yeah, well, first of all, it's a decision that the European Space Agency takes on what sort of programs to put out there where you can participate. For us, this was really good because we could basically apply all these codes and optimizers that I explained to you in the beginning. What we call at some point artificial intelligence that basically puts together the entire rocket and calculates, look, what type of engines, what type of tank wall thicknesses for the lowest possible cost to get payload into space. This entire code, at some point you want to try on different configurations. And this is really why for us, this was a really good proposal to participate, because we then basically had a little bit of money where we could basically say to a couple of engineers, look, guys, you can lock yourselves away and you get the super most exciting project now. Everyone in the company will be super jealous, but you can let these computer codes make something big and basically iterate a larger vehicle. And that's what they came up with. Super exciting overall. And we learned a ton from it, obviously. We learned a lot of the limitations of our computer codes. We could extend them. We could extend the optimizer. We got a whole bunch of quotes in and data points from potential manufacturers. This is key for building something, is to understand the price points that you end up with. And for that, you basically need to come up with some designs. You need to make bigger designs. You need to give them to suppliers. So you get an indication, okay, how expensive will these newer, bigger engines will be? how expensive will the stage be? And long story short, you learn a ton from things like this. Of course, it's not our primary focus, but it was definitely worth it. We always struggle when we decide sort of where to participate and not, because ideally we just want to focus on the first flight, right? We don't want to do anything else. But a lot of my engineers want to do these studies, and in some cases, obviously, in most cases, ESA supports you financially to do these. And I think it's a really good way to sort of improve overall. And to be honest, if the European Space Agency wouldn't put these programs out, we wouldn't ever do them, because I would always say, guys, we have no money, we have no time for this, we need to get to orbit. And this definitely helps us, because we, as management, I can no longer push back and say, don't do it. I get weak and I say, okay, let's do it. Let's learn something, let's improve. And it's definitely worth it. So it was super exciting. You see some of the results. We used the Prometheus engines because in the non-recurring cost calculation, we realized it's the easiest to just mass produce this engine and basically take it. Why would you develop something new from scratch? Again,
Yeah, it's already there.
It's already there, right? And at the end of the day, a lot of the space industry is taxpayers' money. You want to turn every euro into basically a proper investment. You don't want to develop new things that you want to do as an engineer that has no benefit basically for the country and for the continent. And this is the reason why we use that engine here. Worked out super well. The optimizer accepted it. It basically clustered it, as you can see. Yeah, super exciting. I wish this would become real, but the reality is we're not a rocket company until we get to orbit. And this is, again, that's the focus needs to be to get to orbit first.
Yeah, and it will probably take a lot of money and time to be able to get to this point. But as you mentioned, right, like you got to first launch that RFA ONE rocket. I'm still amazed by, you just let a couple of engineers play with this, and suddenly you've got this quite weird rocket. I don't know if you can talk about a few of the things that we saw there, because I see canards on the second stage and like weird landing legs on the first stage. Is that something that like was even looked at too deeply, or was something like, well, we'll put a few flaps here and there and maybe just some generic configuration?
Everything you see there has a very good reason to be there. So the team had the great pleasure to basically go through every single component, size it all, and like I said, use a lot of the codes, the design principles we use to design it all up. But everything there has a reason. Overall, super beautiful. Look at how beautiful this thing is. I want to build it tomorrow, obviously. But again, this had landing legs that were designed in a very specific fashion. I don't want to go into all the details, but overall, super exciting, because something like this, you can basically, you can design a vehicle like this basically in an overall fashion relatively quickly. You can get to the 80% solution relatively quickly. It's then the 20% that comes afterwards that are hard, and it's the last 5% that you need to get it to actually work that is the hardest. And again, this is where typically as an engineer you are, and you realize it's so damn hard. Grass is greener on the other side. Let's build something completely different. But again, the hardest thing is focus and make it work. This is why the first launch is way more important than this. But you can see a couple of details I want to go through. Obviously, also hydrogen. It's quite interesting, but hydrogen and oxygen is basically the best fuel there is. You only produce water. There is no CO2, no carbon emissions. Yes, there's this argument that obviously if it flies to Mars, it's difficult to source liquid hydrogen. This is why some people do methane. For us, hydrogen is the most beautiful fuel. The big question is, can you basically use hydrogen in an easy way, in an inexpensive fashion? We think you can. There's a lot of hydrogen infrastructure in Europe, and surprisingly, if you allow the optimizer to use hydrogen, it will almost always choose it for the upper stages. And it's quite interesting that it will not necessarily choose it for the first stage, because the overall cost comparison in this super complex matrix between cost, performance, and basically payload and then cost to the customer is super complex. But it has chosen basically almost all the time hydrogen here, because that gives you the highest ISP, and ISP is king. It's the most important parameter when building a rocket, and especially on the upper stage, you need it. You need as much ISP as somehow possible. Yeah, you see some of the numbers here. Super exciting. To me, this is like reading through this again. I could read through it every day. Absolutely beautiful exercise. But it's over now. There's like I have to drag people away, lock these documents, make sure no one opens them ever again, and make sure we're focusing on building these engines and improving there as much as we can.
Yeah. One of the other things as well that it was sort of proposing, because it was a proposal from, it was a study for ESA, and so they were thinking, oh, high launch cadence and everything. And I think in one of those, I think it said like 100 launches a year, 150 launches a year, which a few years ago would have been crazy to think about. But nowadays, there's a certain company out there that it's making that reality. So like that's not out of the realm of possibility, I guess. And speaking of launch cadences, because I had that in my mind as we were talking about that, and going back to the RFA ONE rocket, right now, I believe from SaxaVord, I think it's only a limit to launch 10 times, I think, per year. Is that some kind of thing that you got to go through bureaucracy to be able to get higher launch cadence, or is that something that you're not even interested on like, well, 10 launches from SaxaVord, it's okay per year, or like what's that sort of thing that you're looking for?
And the biggest thing for me is to get to 10 launches in general on an absolute scale. If we get to 10 launches on an absolute scale, I'll be the happiest person alive. Look, there's regulations, there's reasons why they only allow 10. But as with everything, you have to look into this reasoning, and you have to convince, you have to make a case to increase it. And typically people want this to happen, right? The cool thing about rocketry projects is that there's not really a lot of people, there's actually no one who wants to stop it. Everyone wants to make it work. But of course you have to understand their regulations, their environmental impacts that you want to minimize as much as possible. So it's totally reasonable. 10 launches a year, to give 10 launches a year to a startup is absolutely reasonable, right? It's actually a far stretch already. In the first year, in the first couple of years, you will be launching a few times a year. So this is not at all a limitation, and that contract and that sort of approval is much better than we were hoping for to get at such an early stage.
Yeah, I'm gonna go to Ryan Caden here for more questions from the chat because I have a few questions as well towards the end here about that specific part. But let's go first to our viewers' questions. And I gotta remind people, if you want to have questions here answered live, you can tag at NASASpaceflight in chat, and Ryan will be picking those up. And so, Ryan, do we have anything in the list?
Bring this one up here from Tio asking, you were mentioning earlier your roadmap towards launch this year. How is the actual kind of progression with your first stage going so far? Is it close to being shipped to SaxaVord, or are you still working on hardware at the factory for the time being?
Yeah, but we basically we are building 2 first stages right now. Unfortunately, can't turn around the camera, but one is very close to completion from a structural point of view. All the welding is completed, and basically now we are basically letting the electronics and the avionics department equip it with all the wiring looms and so on. But we're building 2, and our goal is to ship the first stage in May. The engine production is run on a different timeline. They will try to crank out engines as quickly as possible. Every single engine will go to Sweden, where we do the acceptance test, and then they are shipped independently to SaxaVord, and that's where we actually do the integration. The cool thing about the way we design everything is that we can integrate the engines actually also on the pad. You have seen this last year. When we lifted the stage onto the pad, it only had 5 motors. The other 4 motors could be integrated right in situ there while the vehicle's on the pad, which is very cool. the team has designed a really cool sort of system that allows you to do that quickly. A couple of technicians can do that within a very short period of time. And this is basically how we're progressing. The plan is to have the stage in SaxaVord within May. And then within the following 2 months, we want to receive all the 9 engines to basically be building the first stage and integrating it right there in SaxaVord.
Cool. And one last audience question for the moment. Keith is wondering, SaxaVord is known for being a windy location. I would also say the British weather is famous for being, cloudy, windy, rainy, kind of, not tropical conditions. So how was the weather kind of included in your selection of SaxaVord? Is the weather, the famous British weather, a concern for launching from SaxaVord, or is it just, one of those things, every spaceport has its drawbacks? Is it just one of those things that SaxaVord has that another place might not, but another place might have even worse weather, for example?
Yeah, absolutely. It's something you want to consider. The reality is, you're a really rocket company if you go into orbit once, and you can choose the day when this happens, more or less. So the first couple of launches, they will always be good weather launches. And it's not like there are no good days in SaxaVord. There are some very beautiful days in SaxaVord where there is no wind at all. And this is not a limitation for a first launch at all. It is, of course, quite difficult if you're trying to launch in December. It's quite windy and quite stormy in December. There's a few months where you really don't want to do that. But you have that limitations in a very similar fashion elsewhere around. Look at this image. It's one of the most beautiful places on planet Earth. Fantastic spot to be. For all the listeners who are looking for a job, come and check out the RFA career website. I always say that the best engineers are field engineers that are basically working out there in the field, testing engines, integrating stages, testing stages. And I've been there myself for a couple of months last year. It's a very, very beautiful place to be. And I'm actually super excited to go up there again. And hopefully some of the viewers might join us if we are successful in the application.
Indeed. Fingers crossed we'll be able to get up there as well and bring along those views as well with some pretty cameras. But for now, Alex, I will throw it back to you.
Yeah, one of the last few things that I wanted to talk about, because I guess that's sort of like the thing that not a lot of people want to get into, but it's something that we got to talk about, right? Which is the situation in Europe and the whole spaceflight industry here, which was sort of the whole point of this series of live streams, to be fair, which is, you guys, when that Starship catch happened, that the booster catch happened, you made a reference saying that Europe has completely lost touch. What sort of things do you think need to be improved for us to be able to catch up to some of these other players? Because it kind of seems like we're lagging behind, so to speak.
Look, I think it's everyone can agree that the US is the number one when it comes to basically launching rockets into orbit. I heard the other day that just SpaceX basically per year now is receiving a larger amount of funding than the entire European Space Agency has to distribute on an annual basis in Europe. Not sure if this is exactly true, but this was a statement that I just came across recently. But long story short, look, space funding in Europe is not as extreme as it is in the US. But I think if you normalize it, if you look at how much is achieved with the actual taxpayer money that is invested, you would realize that the efficiency is quite high. And this is, at the end of the day, this is what matters, right? For our society to function, you need to look at resource efficiencies. You need to look at time efficiencies. Efficiency is key for progress, and efficiency is basically the most important parameter to create a functional society. I think Europe is very, very good to efficiently manage and allocate the little space funding that we basically invest. But the good situation is that it's increasing. I think no matter who you ask in Europe, most people that you will meet have understood that basically space is a really important field. Almost every economic process on planet Earth is dependent on space technology. Satellite constellations are monitoring every square centimeter of human activity on planet Earth. It's the #1 technology to prevent environmental pollution. I always say it's like a speed camera, right? You and me, we don't speed on the road because we know there are speed cameras. It's a very similar in environmental pollution concerns. If you know that if an industry knows they're being watched, it's completely different than if they know that they can basically do things without being caught. Long story short, the entire space industry is super important. Everyone understands that, and I think the efforts in Europe are increasing. And that is the good part is that there is an improvement. Of course, Musk is ahead. Great inspiring example on how to basically do this all in such an aggressive fashion. But it's my hope and my hope is, and my ambition is to basically create a European player that can at least capture some of the market there. And I think the key is, again, look at the resource efficiency. We have received very little funding so far. Super glad for every euro that was invested into RFA. But I think from a resource efficiency point of view, this is where you should, this is the parameter you should use to judge if something is successful or not.
Yeah, that is very true. I mean, it's not that we've not done anything, right? Like we are very active in space, and in fact, somebody actually mentioned in chat that we create the service module for Orion. Without that, there will be no Artemis program, for example, for the US. So like we do stuff in Europe. The problem is, getting through and being able to, as you mentioned, use our resources very efficiently. And I guess that's sort of the whole point as well. One of the things that I have last here, which is what will be one thing that I've not asked you today on this live stream that you would like to talk about?
I want to talk about future talent. If you're already said it, sort of, but if you're excited to join us, please check out our career page. You guys can in the chat ask any questions. We always say there are no stupid questions. There are only arrogant answers. A lot of us are deeply invested here and sleep very little. So sometimes we probably do give a quite arrogant answer, but it's not meant this way. Ask away, ask anything that you want to know. Building a rocket is more difficult than you think, right? It looks so easy. It looks so simple. But always remember, the entire vehicle at takeoff, only like 1-3% of this entire mass end up as satellite in orbit. It's incredibly difficult to get to the point where you have a working product, but it's one of the most exciting things. People that work here, a lot of the people that work here, they don't really consider this a job. They consider this basically a fulfillment of their lifelong dream to work on something like this. Super exciting. Lots of spin-off technologies are basically being developed from that. A lot of the processes, manufacturing processes we've established at our suppliers are being used now for other areas in the economy. And long story short, this is just the most exciting thing that you can do, in my view. Super awesome. And yeah, check out that career page. If you want to do an internship, this is the best way to get into RFA. Yeah, that's basically what I wanted to say in the end.
Yeah, and we always allow we always let the companies that we invite here to get that stage open and have a lot of talent that it's true that sometimes we have a more general public, but we also have a lot of nerds in chat that also are studying this, and hey, maybe one of the people that are watching might be wanting to join RFA, so that'd be awesome. We're done with questions, but we did a thing last time that you were here at NSF, which was trying out that mod of KISS, because you were mentioning that your engineers cannot, or at least they're trying to focus on the road ahead on that RFA ONE rocket well, we can play a little bit with that rocket, I guess. And so we have a thing. We actually toyed around with this. I don't know, Jay, if you can show it. There we go.
What is it? You reconstructed the protein proposal, right? That's
No,
what it
I
is.
actually have just the RFA one. I
Yeah,
should have probably done this a lot earlier, and
I
have
thought it's
tried to do
around the
the
corner
protein.
somewhere.
Yeah, right. And maybe next time around I should do that. I
Yeah,
did not
fairing
prepare it.
shape is a little bit different.
Yeah.
Yeah,
Has there been any changes since this mod went out?
Nana,
No, right?
fairing has never flown, but um, we've got 2 sets built.
I'm gonna try it and see if it flies. Like I have actually not tried it yet, and I don't even know if it's gonna crash or not. Not the rocket, but the game. Ah, there we go. It's loading. So yeah, this mod you guys released it I think a few years ago, right? And
Yeah,
it's sort
yeah,
of with all of the engines and everything here. And there we go. Look
there we
at
go. The first flight. We are operating with a quite large thrust to weight ratio. That's a difficulty to actually estimate thrust to weight ratios in rocketry at takeoff. If you let the optimizer choose, it will put it at 1. Obviously, at a thrust to weight ratio of 1, it's almost impossible to take off safely. Yeah, the first stage here burns for roughly 3 minutes. And you've got 9 engines. Thrusting, we can lose 1 engine right at the beginning. So we have enough margin for this first flight to lose an engine straight away. That for us was super important. There's this big question, is an engine cluster more reliable than a single engine? The answer is it depends how you do the systems engineering and the designs. If you don't do it right, you end up in a situation where definitely 9 engines are less reliable than a single one. If you do it properly, if you do the systems engineering right, you can show mathematically that 9 engines are actually offer some redundancy. It's quite interesting that the later part of the first stage flight, you can lose a lot of engines without losing payload. If you lose engines and you don't lose propellant, if you basically you keep the propellant to be burned by the other engines, and overall the payload losses is quite insignificant. This is an interesting one for a lot of the engineers that when they learn about all the engineering sensitivities that we run. But basically, in the end of the flight, you can lose quite a lot of engines. You somehow need to keep a minimum acceleration to basically consume all the hot propellants. Liquid oxygen heats up very quickly. At the end of the flight, it's very often close to 100 Kelvin, and you really need this acceleration head to make sure that you can use it all. It's one of the most difficult things is to complete the burn of the actual stages. You want to basically use up every single pound or liter or kilogram of propellant before you shut down the engine. Then staging, obviously you've just seen the first to second staging, super difficult also. It's super difficult because you stage the vehicle and then the pusher basically, all the propellant settles on the bottom because you push the stage, but then the stage still has quite a lot of drag. Not a whole lot of drag, but enough to basically for the propellants to slosh forward, and basically you then have helium at the engine at the second stage engine to ignite. It's quite important that you design the system so the engine actually can ignite the second stage engine. The interesting part about second stage engines is that it's all about ISP. It literally doesn't matter much what the thrust is. If you look at all the sensitivities, the engine size on the second stage is not a strong design driver. If you would put 2 or 3 engines on, the actual payload would not change very much. The optimizer would put the propellant distribution into first, second, and third stage a little bit differently, but overall the payload wouldn't go up significantly. It's second stage or third stage engines are all about ISP. First stage engines different. You want the first stage engines, you can do a lot with thrust to weight ratio. On the second stage and third stage engines, you can't use that parameter very effectively.
And now there's
I'm not
here
sure
a
what happens
thing.
here. This is a mod that
Yeah.
is definitely old because there's a coast. For our current trajectory, there is no coast between second and third stage.
You just inject directly?
We basically stage. There's roughly 5 seconds before
Okay.
engine ignition of the third stage. Again, you have third stage has the same difficulties in engine ignition than the second stage after separation, but it has no drag anymore, so somewhat easier to stage and start the engine than the second stage.
Yeah, because that's one of the things that we didn't touch on, that you guys actually have this third stage as well
Yeah,
on the
absolutely.
RFA ONE rocket. And
It's a result of rocket scaling. If you make rockets smaller, you need to add stages, otherwise it becomes impossible to do. If you're trying to build a small rocket with 2 stages, it's close to impossible to get to orbit. You want to, for the first couple of flights, you want to make sure that you have a healthy DV margin. We roughly have 1 kilometer per second of DV margin on our nominal trajectory. You need about 7.5 kilometers per second to get into orbit. We have about 1 kilometer per second of DV margin that we basically not allocate payload on, so that we can basically increase margins everywhere. Like I said, the first one is choose a higher thrust to weight ratio. Then don't make the staging so aggressive. Don't make the engine up and down throttle so aggressive. Don't put the requirement on that you have to use all propellants down to the last kilogram, but basically be happy with having a little bit of unburned propellants, making sure that the OF ratios don't have to drive into the extreme corners of what the engine can do, and so forth. Long story short, in the second stage needs to reignite. Our second stage has basically storable propellants, but storable propellants that are not poisonous. Super important for us. It comes down to cost. If you use MMH or UDMH, you typically end up in very, very expensive hardware because of all the occupational health and safety around. Our third stage uses nitromethane and N2O. Long story short, the injection on this first, the orbital injection on this first launch attempt is quite elliptic, and to basically circularize the orbit, the second stage has a coast. The third stage is coasting around after it's burned for about 45 minutes, right? Roughly half an orbit, and then it's basically has a very short burst. I think it's right now roughly 30 seconds to basically turn this orbit circular. It's important. We want to go to orbit. We want to go to orbit on this first attempt. But if that, like just hypothetically now, if the third stage doesn't reignite, it would still be orbital. It would just be on an elliptic orbit, not on a circular one. And then the cool thing about this third stage, obviously, is also that it stays there. It stays there in orbit, and you can always use it for scientific missions. You can equip it with solar panels, and you basically have a free spacecraft for someone. So if there is a technology demonstration project where basically the customer really just wants to put the payload on, they don't want to develop a satellite, they can use the third stage, and they can continue to operate the third stage once it's in orbit. Again, it's basically for free with every launch. And obviously our big ambition why we have this third stage and why we will continue to use it also for future vehicles is that we have this vision of basically, it's like in the Scouts, you learn that you leave a campground cleaner than you found it. And our sort of long-term vision is that this third stage is staying in orbit until it basically identifies some space chunk, catches it, and deorbits with it. Because the reality is, at some point, you have to change your focus towards not just mitigating debris, but actually removing debris, space debris from orbit. And think about a vision, or think about the future where a launch vehicle will actually actively remove space chunk, not contribute to it. And this is possible here because, again, the third stage now is in orbit. It ejects a satellite, and the orbital stage itself has a lifetime of roughly, we target 5 years in orbit. for the for the early versions, not for the first flight, but the early version. And in an ideal situation, the orbital stage now has 5 years of time to wait and dock to a piece of space junk and actually deorbit that, so that the net positive launch service is space debris negative. You basically, with every launch, you reduce space debris. You don't contribute to it. This is at least this is the vision we have. It's super difficult. Obviously, if you're traveling at 7.5 kilometers per second, you can imagine how difficult it is to actually dock to a piece of space junk, capture it, and deorbit it. But the reality is, as technology moves along, we will definitely be able to do that at some point in the future. And I hope that I will live long enough to get to the point where we can say, look, we actually remove more space junk with every mission than is generated.
Yeah, and I was actually that sort of profile that I did there is sort of like coast phase, then you relight with a third stage, circularize the orbit, deploy the satellite, and if I remembered how to do it, I will probably come back to the third stage and do the deorbit burn, but it's already a lot of work. I'm not the guy that needs to do this, of course, but you know, it's really neat what you mentioned, right? That you know, there's a lot of stuff up there, and it's true what you say, that we need to make sure that in the future these things do not actually stay there. But you know, I think we're probably coming up on the end of the show. It's already been 91 minutes, which is probably our longest for this series of live streams.
No problem. No problem on my end. Look, obviously super important to create some excitement around here. Building rockets, for me, there's nothing more exciting. There's also a lot of things that you can do to improve life on Earth. Space technology can help us in almost every single facet. And I appreciate that you took time to go through some of these questions with me. And I hope I could create some excitement. And I also hope that some people that are making a career choice are choosing STEM and are choosing space. We need more people that work in technology to make life more sustainable. This is the key message I always have. We need more people to actually tackle the big problems that we have. There's a solution for every problem. It's just super difficult to find a solution, right? As we become more technological, sometimes to a lot of people it feels like it's impossible to solve something, but it isn't, right? There are new ideas, there are new ways, there are new technologies to solve problems, and you can best do that if you choose a career in STEM. And obviously, space is one of the most exciting things you can do with your life.
Yeah, definitely really cool. I mean, it's rockets. Like that's the edge of our engineering, I guess, of how we can put things in space and we can improve the lives of people here on Earth. And yeah, Stefan, really thankful for this interview, for you coming here to NSF Live, and hopefully you come back maybe after the launch. I don't know, like another time later in the future, of course.
I think it's been roughly 2.5 years. I talked to some of the people here before, and I realized it's been 2.5 years since we did the last interview, and that created sadness inside of me. I aged 2.5 years, still not in orbit, but it will come. So hopefully next time we talk, we have something in orbit.
Hopefully. Fingers crossed. But yeah, and also thanks to members for making all of this possible. Of course, we wouldn't be able to do this without your support. Here's all of our launch directors and flight engineers, the higher tiers of support from our members on YouTube. And of course, thanks to Ryan for taking all of those questions from people watching live at home or whatever you guys are watching from. And thank you, Ryan.
Yeah, I have to say, in the queue here, like usually on these shows we get a couple questions like, oh, how can I apply, how are you doing internships, you know, stuff like that, how do I join the team? Like literally every other question in this queue right now is how can I apply to join RFA? So Stefan, I think you've definitely succeeded in generating excitement around what you're doing.
Very cool, very cool. Thanks guys for helping me, and yeah, super excited to talk to you again in after first launch.
And of course, thanks to Jay as well, because, you know, all of this is running thanks to his producing of this show. So thanks, Jay Keegan, for that. And of course, we're going to have a lot more shows coming up. So stay tuned. And of course, as always, thanks for watching. And until the next one, see you later.
And here we go.
We have liftoff.
Propulsion continues to be nominal.
R68 chamber pressure looks good.
Following up. Roger, Atlantic.
Water towers, fly! Yes!
Tango down to nominal. Flight downside FT off. Bring in FT off. It's orange!
R45! Oh my god! Oh my god!
Decollage.
What is it?
Put that in the big bag,
343 unfolds to go.
Indeed. We rise together, back to the moon and beyond.
The methane will be igniting in the flare, correct?